Hi, I'm Ben, and I want to show you a clever method that lies at the intersection of math and physics. This video will start with an overview and demonstrations of the physics, then develop how mass points are used to solve geometry problems. Let's start with this triangle. Today, I want to consider not the physical triangle, but a three-body system of masses located at its vertices. For our first example, let's start with masses of 4 coins, 2 coins, and 3 coins. The question is, can we locate or construct the center of mass of this triangle? Right? Can we find the point at which it will balance? We can construct the center of mass using the law of the lever. Around the year 250 BCE, Archimedes stated that for a lever to balance, the product of force and distance on each side must be the same. For example, a weight of 2 coins placed 3 units away will balance a weight of 3 coins placed 2 units away. Or if I double the left stack to 4 coins, with twice the weight, I can halve the distance to 1.5 units. I've drawn out our triangle with the vertices and masses 2a, 4b, and 3c. Consider segment AB and its balance point F. Point F must be twice as close to point B because there is twice as much weight at point B. Using the law of the lever, 2 times distance AF equals 4 times distance FB. And we can solve for the ratio AF over FB equals AF over FB, 4 over 2, or 2 to 1. This ruler represents segment AB and its balance point F. Note it balances when the distances are in inverse proportion to the masses. So I'm going to take 4 coins and put them 2 units away, and 2 coins at 4 units away. And then the distances will be in inverse proportion to the mass. Another thing to notice while we're here is we can move all 6 coins to the fulcrum. The system still balances, and it still feels just as heavy. If I shut my eyes, I can't tell the difference. Okay. Back on the diagram, I can assign a mass of 6 to F. The 3-body system has been reduced to a 2-body system. 6F and 3C. Using mass point notation, I can write that the system 2A plus 4B plus 3C is equivalent to 6F plus 3C. Let's now balance those 2 masses along the segment FC. F has a mass of 6, C of 3, so the balance point must be twice as close to F. We'll call that 9p. Okay. This point is the center of mass of the original three-body system, 2a, 4b, 3c. We found this center of mass using ratios along AB and FC. FC is called a Chavian. A Chavian is any line segment from the vertex of a triangle to the opposite side. I can draw the other two Chavians from vertices A and B through P. And we'll assign these feet letters D and E. If we had balanced along BC, there would be a mass of 7 at D, and if we had balanced along AC, there would be a mass of 5 at E. There are now 6 divided segments in the diagram, 3 sides and 3 Chavians. Mass points can be used to solve for all 6 ratios. Let me write them out. So on segment AB, AF to FB is in the ratio of 4 to 2. From foot F, FP to PC is in the ratio of 3 to 6. From side BC, BD to DC is in the ratio of 3 to 4. And DP to PA is in the ratio of 2 to 7. And on the last side, AC, we have that AE to EC is in the ratio of 3 to 2. And from foot E, EP to PB is in the ratio of 4 to 5. Here is the physical system. The balance point of the triangle splits the Chavians into the expected ratios. Now, the power of this method of mass points is that it can be done in reverse, applying physical intuition to solve geometry problems. Given any triangle and an interior balance point P, if 2 of the 6 distance ratios are known, then 3 mass points can be determined and the corresponding other ratios can be solved for. Here is an example. I encourage you to try the problem on your own. Since we are working in ratios, the first mass you choose is arbitrary. Try a starting mass point of 5a, then see if you can find the other 2 masses and remaining ratios. Pause the video now and then resume to see my solution. So with a mass of 5 at A and a ratio AT to DT of 3, the masses must be in inverse proportion, so we'll put 15 at D. And balancing on segment AD, there's a mass of 20 at T. Then BT to ET is 4. So there are 5 parts of 20 in a ratio of 4 to 1. So B must be 4 and E must be 16. That is, B is 1/5 of 20 and E is 4/5 of 20. And the masses are inverse proportion to the distances. Finishing, we want to solve for what is the ratio of CD to BD. Looking along segment AC, if it balances at E with a mass of 16, C must have a mass of 11. And then we can finish the problem. The masses are in the ratio of 4 to 11, so CD over BD must be in the inverse ratio, 4 to 11. Now, some caveats. Careful listeners will note I'm saying things like identifying masses consistent with these ratios. I've been avoiding saying we've solved the triangle. Here are several different triangles with the same mass points. So what's going on here? It's important to remember that these mass points are not dimensions on the triangle. Rather, they are a set of 3 numbers that encode distance ratios within 6 sets of collinear points. Various transformations will preserve collinearity and ratios. These are called affine transformations, which are a deep topic beyond the scope of this video. In practice, when using mass points to solve a particular problem, either enough extra information is given to specify the triangle fully, or the answer relates to a ratio that doesn't require the triangle to be unique. I'd like to end with a more sophisticated situation, one that uses the physical intuition of balancing more creatively. I'll present an example going forward from masses to ratios, and then leave for you a problem to try the reverse process, going from given ratios to identifying masses consistent with those ratios. For my last example, I will load 4 masses onto the 3 vertices of a triangle. This results in one vertex having 2 coincident masses. The total mass of 3A has been split into 1A1 plus 2A2. Let's now locate the center of mass of the 4-mass system. The masses at B and C may be replaced with a mass of 7 at the balance point along BC. This mass point, 7D, is located 4/7 of the way along BC. Now, the balance point between 7D and 3A is the center of mass of the system. Alternatively, we can locate the same center of mass in a different order. Starting with A1 and C, the mass point 5E is located 4/5 of the way along segment AC. Then, on the right side, the balance point 5F is located 3/5 of the way along AB. Because the masses at E and F are the same, the center of mass of the system is located at the midpoint of segment EF. What have we accomplished here? Note, using 4 masses produces an intersection of a Chavian and a transversal. Working backwards, the technique of split masses will be useful in such situations. For a further challenge, I'll point you to a problem from the 2009 American Invitational Math Exam. This is one that you can try to solve on your own using the technique of split masses. In summary, mass points is a method that uses physics principles to solve geometry problems. It's powerful to take tools from one realm and use them to solve problems in another realm. I'm thinking of things like Andrew Wiles applying topology techniques to solve a famous problem in number theory. Or maybe at a high school level, transforming a problem that doesn't involve a circle into one that does. Then circle formulas can be applied to crack open the problem. As you do more math and physics, you learn to use more and more tools. I wish you the same joy that I have in finding that you can use these tools in unexpected places.